Hello, my name is Will Schultz. I'm here from New York City. I work as an engineer at a database company in New York, and today I'm going to be talking about an animation module for TLA+. So, to motivate a bit about the animation module, why I created it, what I think it's useful for, I first want to look at the question of what specifically TLA+ specifications are useful for. I think this was definitely touched upon a bit in David's talk, and I'll talk a bit more about it now. So in my view, I think there are three, in my experience, three main valuable aspects of writing TLA+ specs. One of them is about communication. If you have an idea or an algorithm or a system and you want to describe it, you have a way to codify it in a precise way, in an unambiguous way, share that with other people, whether it's one person or I know in my work, often a very hard problem is sharing ideas and making sure that the precise details aren't lost in those communication channels. So I think that's one big aspect of TLA+. The other is learning, which again, I think David talked about this, is that this is often probably a personal process. I know in my experience, I think that the intellectual process of writing a spec simply forces you to think precisely. It forces you to think more abstractly about what you're modeling and often come to a better understanding of the system or the algorithm you're trying to model and describe. And I think that's, again, a distinct aspect from the first, which is communication. And lastly, of course, is the verification aspect. Once you write a spec, you can verify it either using the model checker or the proof system as well. I personally haven't worked much with the proof system, but this is a clear, valuable aspect, and some might say sort of the more pragmatic aspect of writing a spec, but obviously the first two are immensely valuable as well. So I bring up these 3 points because I think the animation module attempts to enhance the first two. It doesn't try to address the issue of improving or enhancing the verification process at all. It looks at the first two and tries to see how those processes might be improved. So if we look at the current state of TLA+ for the communication and learning processes, again, this is in my experience. There might be other ways to do this, but the communication process, one way is basically you write a textual spec, and when you're finished, or when you're partially done, you give it to somebody else and they read through it. And that, depending on the complexity of the spec, might vary in terms of how laborious that is and how much time that takes intellectually to invest to understand the spec. And I actually think another approach here is giving someone, along with the spec, an associated model or parameters of a model. I know I've done this to test out specs or try to understand a spec that I've downloaded, is to open it in the toolbox, define a simple model and explore, see what kind of traces it generates, maybe generate a few random behaviors or try to check some more trivial invariants to produce behaviors to see how the algorithm or the system works in general. In the learning process, I personally view it as a cycle. I have this to say: think, write, verify, and then iterate. If you decide you want to sit down and model a system or an algorithm, you just have to start thinking about what you want to describe, what you want to build, and then accompanying that, at some point you will start writing, whether that's some prose, some comments maybe, and then some TLA+ as well, to start formalizing what you've been thinking. And I say this is a cycle because I think these always feed back into each other. You might sit and think for a while, write a bit, and realize then how your thinking was incorrect or misguided in certain ways. And I put verify in there as well because I think in this process, the existing tools, I would say mostly the model checker and the toolbox along with that, I think is often a useful part of that process of you, again, as a check for your thinking as you go, for your thinking and your writing, to act as a sort of debugger for your thinking and modeling process. So the main thrust of the animation module is to say, how can we use visualization as a way to improve these two processes? So the communication process and to enhance the learning process of writing TLA plus specs. So that sort of is the broad motivation for what this thing is about and why it's worthwhile. So now I'll talk a little bit about what it is, how it works, and then I think most compelling is just to look at a few examples of animations that have been produced using it. So the basic idea is very simple. It's just to take execution traces produced by TLC and visualize them as a sequence of frames, basically. If we take any behavior that's a sequence of states, we simply produce a view of each state, which is some graphical representation of that state, and compose them into a sequence of frames to produce an animation of that behavior. Yeah.
When you say view, are you talking about TLA views defined TLC or something else?
I might have to come up with better terminology because it's not the same thing. But I actually sort of thought that maybe was what that was when I first learned about it, but it's something different. This is a view and just in the context of this animation module. Yeah. So the basic structure of the module, again, it's just a TLA plus module. So it just defines operators to describe and lay out graphical primitives. It's basically based around SVG. It's all the same attributes and basically the same elements. So you could, create a circle. The implementation there is not important, but that's just the basic idea. And similarly, you can group together elements, basically all the things you could do with SVG elements that you would do in a browser. And then the main concept is this idea of a view expression. So this is the main thing that you as a user of this module would need to define to produce an animation. It's just a TLA plus state expression that just takes a state. It's sort of like a function. It's really just an expression, though. It just depends on variables in your spec and perhaps any constants as well, and produces one frame, which is just a composition of graphical primitives that represents a visual representation of a particular state. So I'll first go through basically what is a trivial example of how you would use this module just to understand the basic ideas, and then I'll give a few examples of more non-trivial specs that have been animated using it. So this is just a basic. Hopefully it's large enough. There's a next slide that will zoom in a bit to show the parts a little bit larger. But this is just a basic trivial spec with 3 parts. So we could see this as just a basic spec. This would be, for example, the way the animation module is designed is that it's basically built to say you would have some existing spec that lives on its own, and then you just create what we might call an animated version of that spec, which just uses the definitions and operators from that original spec. So in this case, this could be the basic spec that we start with that describes some model or system. Just has 2 variables. Again, it's just trivial to demonstrate. And one or the other can increment by 1. So in this case, we then have a view. So this portion of the spec is a view, expression, and associated definitions to accompany it. And then we have what I call the animated spec, which is a new definition, which you can see depends on the initial state and next state predicate from the original spec, from this basic spec that you started with. I'll zoom in a bit to go into more detail. So the view, as we can see here, again, just a basic example to demonstrate how this works. It's just an expression. We just have a little bar chart that just represents the magnitude of these 2 variables. Each is a rectangle with certain parameters. As we can see, it depends on the variables and some constants, and they're put into a group element. And then the animated spec, we see this animated init and animated next. Those are basically operators that are defined in the animation module, and they take as arguments your original init and next state predicates along with your view expression. This is another feature which I'll discuss later on, but it basically is a parameter that allows you to, related to the fact that you're also, it also allows you to annotate actions that your specification takes, basically a way to provide a named identifier for a certain action when you produce the animation, which we'll see later on. So some of the module internals, again, I'll at the end give a link to the code, the module itself, and examples. But basic idea is that it defines a set of auxiliary variables internally to track animation-related state, and then it uses these variables to just record a sequence of frames. So every time an action occurs, it basically appends the new frame to a sequence of running frames. So there's overhead involved in this, but that's the basic idea. Uses the view expression to produce each frame. And then when the trace generation finishes, for example, using if an invariant was violated, generated by TLC, the final state of that behavior basically contains the full animation. And it's basically just a string for now that you put into some HTML template that you can view in the browser. Okay, so now I think this is the more interesting part. I'll jump to a few demos here. And yeah, so I'll explain why I think what example in this case, what it illustrates about enhancing those two processes, the communication and learning processes. And I'll describe a bit about the specific algorithm that these examples are visualizing. So these are both examples based on an original TLA spec. I'm not going to show the textual spec here because I don't think, for sake of time, it would be worth doing that. But I'll try to explain as much as you need to know. So this example is pretty simple. It's called log visibility. It basically is, this specification, I would say, is more an example of illustrating and codifying a relatively simple concept, but something that's subtle and interesting enough to actually formalize. So this concept of log visibility, I'll give some background. It's this idea that in a transaction processing system, database, you might have many transactions executing concurrently, but you want some way to record the execution of these transactions into a sequential log. Basically, this log ends up being some valid serialization of the transactions that executed. But in real time, these things are executing concurrently, but you want to put them into a serial log, but without serializing every transaction, literally. So this idea of log visibility is that what we do to give transactions positions in the log, as we can see, this represents slots of a log. We just give them integral numbers here. We assign each transaction at some point in its execution. We can call it a timestamp that defines its position in the log. But that the assigning it a timestamp doesn't necessarily, the ordering of timestamp assignment doesn't necessarily match to the real-time commit order of the transactions. So what we see here, I'll sit down just so I can more easily step through here. But what we can see here is basically every log slot can go through, as in this little legend here, a number of states, pending, committed, aborted, or available. So pending state represents a transaction starting. So we've assigned a particular log slot to a transaction and said, transaction, you get to go in this log slot 0. I'll just step through a few steps to give you an idea of what's happening here. Again, this is very simple, but it illustrates a certain concept. So each transaction, I'm stepping backwards now, you can see the frame number there, along with, as I mentioned before, the annotation here, which says what is the next action we're going to take, which is just a string that you can define. So we see log slots changing their states, and we have this visibility point. And basically what the visibility point is about maintaining the highest position in the log such that everything behind it we know is committed or aborted. Basically, the point at which there are no holes behind you in the log. Basically, this concept can be important for one example if you want, if you want to ship these logs to some other node or some other server, but you want to make sure that after you've shipped it, no new transactions complete in a previous slot. And so we maintain this notion of what the visibility point is in the log. And as we can see, when transactions commit, so in this case we have 2 holes in the log, and somebody commits in 4 but is not committed in 3, aborts in 4. And as soon as we filled in 3, then we can jump the visibility point forward, and so on. So this is a pretty, I'll jump through again, but this is a pretty basic example, but I think it illustrates what I talked about before, is that you can start to get an intuitive sense of what this concept is, where if I handed you a textual specification, or even a model maybe, I think it would take some time for you to say, what are the parameters, what should I set these constants to, and then you'd basically probably want to either read the comments or the spec or read through textual TLC traces, whereas I think this is perhaps a better intuitive start to understanding what's going on here. Any questions on that?
How big is the animation section of the spec for this example?
You mean like how many lines?
Yeah.
At the end, I'll show the animated version for each of these to give you just a rough sense of how big they are. It varies, but yeah. This spec itself is pretty small, so the original spec. Okay, so that's one example. This is a second example that I think illustrates a somewhat different concept, which is how, again, on the communication side of things, how to show or demonstrate a particularly subtle error trace that an algorithm can produce. I think Valentin mentioned that one of his traces was 150 steps long, and just this notion of how would I communicate that to someone else? I either give them the text, or again, you explore that in the toolbox, or perhaps you encode the invariant violation as a predicate. But again, I don't know if that always gives you an intuitive sense of how the execution got to that state. So again, without describing all the details of this algorithm, the basic idea here is this is a visualization of the Raft consensus protocol. It's a consensus protocol basically for maintaining a consistent log between a set of nodes in the same spirit as Paxos, or Raft is just sort of a more modern take on that. So Raft is a leader-based consensus protocol. So at any one time, nodes can essentially be in follower or leader state. And leader is the node that's responsible for accepting client requests, serializing those entries into a log, and then replicating those log entries to other nodes. And I'll sort of like step through as I talk, just to give you a sense of just what these things look like. I think that's actually more important for these examples than for right now understanding all the nuances of the algorithm, just to get a sense of what this type of visualization would, how it would give you insight into a particular algorithm. So basically what this trace, again, I don't expect us to go through all the rules and subtleties of the algorithm, but this trace that we're visualizing is basically a particular edge case of Raft, which I think is illustrative of a particular property of the algorithm. And that property is that basically we can see each node has a log of entries, and Raft has this concept of a term, which is basically a monotonic counter that every server maintains. And there are rules about when you increment that and things, but basically the idea is that there can only be one leader per term. Again, don't worry too much about that, but we see the term there in the log of a particular node. So the interesting property of Raft is that you can end up with a particular log entry replicated physically to a majority of the nodes, a quorum of the nodes, which in this case is 2 out of 3. But that doesn't necessarily imply that that log entry is committed in the sense that it will never be erased from that slot. And this is perhaps somewhat unintuitive and different from other systems, Paxos-based systems, where you simply need basically an entry to exist on a quorum, a majority, most often, for it to be considered committed. So again, I'll step through fairly quickly, but again, what's probably interesting to observe is just having a visual way to represent the state transitions here. And the most interesting thing is probably to see who's a leader here. You can see the little L, F, which represents the states and also the color of the nodes. Also represented in here, this is a distributed algorithm. This is one approach I had to visualizing message flows, which is simply giving each node basically an inbound message queue, and that's what we see appear next to each node. So this represents a message that, for example, is sitting on your incoming queue but has not been processed yet. So we see a series of transitions, leader changes, and the interesting part to note is when we get to a particular state here, which is where we see that first log entry on N0 and N1 now exists on a majority of nodes. And now, as we continue stepping forward, the interesting part will be to see that ends up getting erased by a particular sequence of actions. So eventually, we will see node 2 become leader once again, and basically forces N1 to come into alignment with its own log and erases the entry at position 0.
To steer to this edge case, did you have to like modify the spec a little bit, or?
That was a tricky part, and so I coerced it a bit for TLC to produce this particular trace because it's a particularly subtle and long trace. So that's, again, I don't expect you to take away everything, all the details of that, but this was another example of a particular use case that I think is compelling, which is these things are just there's a lot of detail and complexity to communicate here, and to communicate 70-some states to someone else is a tricky thing to do. And I think this is another application of how animation would help with that. So with that, I'll wrap up with just some concluding thoughts and then some questions if there are any. So let's stand up again. So this was inspired somewhat by other tools that definitely exist already for animation and visualization. I know the ProB animator tool seems fairly fully featured. My goal in this was primarily to build something that was sort of native to TLA+. As far as I know, I haven't used the ProB tool much, but as far as I know, you would have to translate specs to be models first to animate them. And also there's a tool called Runway, which was developed that's sort of a specification language along with a visualizer tool, which seems somewhat interesting, but I don't think it's really actively maintained any longer. And again, it's not based on TLA+. Also, for improvements to this, improving the performance, which might be helped by closer integration with TLC, if this was something that was interesting enough to pursue further. Right now, there's a lot of auxiliary state that's basically just tracked using strings and things, and so it's not really feasible to do a lot of this alongside serious model checking because it'll just slow things down too much. But I used it right now as sort of I personally like the random simulation mode a lot, just to get a sense of what behaviors might even be generated by a spec. And that, as far as I understand it, is a little bit much lower overhead than a full state space exploration. Another thing is fully interactive trace exploration. Basically, this is something that the Runway tool offers. Right now, it's just you produce one trace, and that is what the animation shows. It would be interesting to have a way, again, probably with TLC support, to, at each state, you could interactively select what action you want to take to basically manually explore the state space yourself. Yeah, that's basically it. And so the module itself and the accompanying examples are at a GitHub page that you can take a look at. There's some documentation about how to use it. Yeah, that's all I have. Thank you.
Thanks a lot.
Are there any questions?
So in the module, does it provide any support for higher level layouts and so on? I know from working with JavaScript libraries like D3 and so on, you can produce great stuff, but it tends to be a non-trivial amount of work just to move everything around and get it set. Do you have any higher level either layout or even fancy sort of constraint-based stuff which would do that for you?
No. Right now, I tried to keep it pretty simple, pretty bare bones, partly for the fact that I know that things like D3 are very powerful, but also fairly complex. And so I didn't want to bake any of that in. I started very simple with things like just a grouping construct. And I got fairly far. I didn't feel like it was doable with a little bit of cleverness. And also I think actually the expressiveness of the language itself helps because you're just writing things in TLA+, you can do clever things there. So yeah.
From what I can tell, the animation information is now part of the trace itself, right?
Correct.
Have you tried taking a TLA trace as is and then imposing the view function on top of that? And if so, why doesn't that work?
Yeah. No, that's a totally valid approach. I think an alternate approach. I had thought about that. It may end up being more like the better approach long term. Mainly because I didn't want to have to build tools for parsing traces and understanding all different, how you parse a record versus a function. And so I didn't want to go into that. And there might already exist code in the toolbox and things in TLC that actually does that. But I didn't want to go down that path. This felt a little simpler in certain ways that you can just define things right in TLA+. You also don't have to work in like more than one language. Like if you kind of parsed it and then maybe visualize things with JavaScript. So that was my thought on that, yeah. Yep. Cool. Oh, yeah.
So you have to draw all these states, right? How much of graphical language should I know in order to do that? It's like, you mentioned this SVG, right? How complicated is it?
The examples you saw are basically produced using, at this point, 3 or 4 elements, which is a circle, a rectangle, and a text element, and a line maybe. And they have X, Y positions and attributes. And that's basically, there's nothing more complicated than that right now. And there's a grouping construct, and that's all there is right now. Yeah, I kept it explicitly bare bones. Yep. To Ron's point too, there, sorry, I didn't show the examples, but you'll be able to see the examples at the GitHub. Yeah, so, yep, cool. Great. Thank you.
Thank you very much.